All right. Hello, class. Um, are doing well this afternoon. I just wanted to make 100% clear that the grade changes that you observed yesterday were an April Fool's joke. You do not have minus 1 million, minus millions of percent, or plus millions of percent. Okay. So no need to panic. Believe it or not, I got a number of panicked emails from students who thought I was completely serious and that they actually deserved. But you know, um, let's see, who do we have watching today? Hi, Zach. Hi, Justin. Hi, Rowan. Hi, Rourke. Hi, Christian. Hi, Elite Pro. Why did I forget who Elite Pro was again? I forgot again. I know I asked who Elite Pro was, but hi, Mina. Hi, James. Hi, Alex's W's. And hi, Stephen. Hi, Alex A. Etc. So what are we going to do today? We're going to learn some. Oh yeah, Mohammed. Hi, Mohammed. So I'm going to think about it as Elite Mo. That'll help me remember. Elite Pro is Elite Mo. All right. So we're going to learn about some more complicated LR circuits or RL circuits or whatever you want to call it today. To start off, I wanted to remind you about V equals L di dt. This is the voltage across an inductor. And an important point is that after a circuit has been going for a long time, I will settle into a constant. So if the current is a constant, then the voltage is 0. Okay. Which means that the inductor basically becomes a wire. Okay. So, all right. So the inductor is basically a wire after the current has been on for a long time. So what if we had a circuit that looked like this? All right. And let's say that this is 2 ohms and this is 2 ohms. And this is, I don't know, a 6 volt. Okay. On for a long time.
You be quiet, bug. Knock it off.
Hey, Aisha.
What did I say?
All right, so I can't even remember. Okay, the circuit has been on for a long time. So what's going to happen is, you know what, just for fun, I'm going to put a resistor in here too. And this is going to be a 1 ohm resistor. So if the circuit has been on for a long time, the inductor is basically acting like a wire. So we could think about the circuit as just being this. Okay. Without the inductor. And this is 1 ohm, and this is 2 ohms, and this is 2 ohms. Now, if you were to find the total resistance of the circuit, it would be you see these two are in parallel, so they would make 1 ohm, and then those are in series with this one. So 1 ohm in series with 1 ohm equals 2 ohms, which means that the current is going to be 6 volts divided by 2 ohms. That's 3 amps of current. Okay? So 3 amps of current is going to be coming out of the battery. All right? And you can see that there's 2 ohms this way and 2 ohms that way because each branch has equal resistance. They're going to split the current equally. So this branch will get 1.5 amps, and this branch will get 1.5 amps. Okay? So I could say that the initial current through the inductor is 1.5 amps. Okay? So kind of like you might remember when we were doing RC circuits, we had to figure out what was the initial charge on the capacitor. In an RL circuit, we have to figure out what is the initial current through the inductor. By the way, why did I say that the inductor is going to have the same current as the 2 ohm resistor? It's because it's in series with the 2 ohm resistor. All right. Okay. The other thing I wanted to say is the time constant in an RL circuit is L over R. Keep in mind that this is the resistance that the inductor sees. So for example, it could be 2 resistors in parallel, or it could be 2 resistors in series. All right. So for example, if this were the circuit, then the inductor is discharging through the parallel combination of those 2 resistors, and so the time constant. Let's do an example. So let me draw this circuit. It's a pretty big circuit. So let's say this is 5 ohms, and this is 2 ohms, and this is 12 volts. Oh, I'm going to make these kilo ohms. Kilo. And let's make this 6 kilo ohms. And let's make this 11 is in the left position for a long time. At t equals 0, it is moved to the right position. Find the current as a function of time. Okay? So when the switch is in the left position, you can see that this right part of the circuit is completely eliminated. Boom. So all we have is this part. Okay. And if we look at it, if this circuit was in this position for a long time, then the inductor has basically become a wire by that point. Okay. So the circuit, after it has been in the left position for a long time, the inductor becomes a wire. So we literally just have that circuit. So how much current is going to flow out of the battery in that case? It's going to be V over R. So it's going to be 12 volts over 6 kilo ohms. So what is 1 over a kilo? That's 1 over 10 to the third. That's 10 to the minus third, which is also known as a milli. So we're going to get 2 milliamps of current. Now, if we look at this resistor, the resistor is in series with the inductor. So our I naught is 2 milliamps. Okay? Now let's think about our time constant. What about when the switch is in this position? We ignore the battery now. The battery is out of the picture. And we can see that the inductor is discharging through the parallel combination of the 2K and the 5K resistors. So the resistance that the inductor is going to see is going to be 2K in parallel with 5K, which I will spare you the math, is going to be 10 over 7 kilo ohms. Is the I initial, Christian asked the question, is the I initial always based on what resistor is in series with the inductor? Yes. And whatever the inductor is in series with, that is going to be your current, okay? I think that's a good question. I'm going to go back to one where I think it's tricky after I'm done with this problem. So 10 over 7, that's about 1.4 kilo ohms. So that means that the time constant is L over R, which would be 11 microhenries over 1.4 kilo ohms. So what is a micro divided by a kilo? Well, a micro divided by a kilo, a micro is 10 to the minus 6. A kilo is 10 to the third. So we have 10 to the minus 6 divided by 10 to the third, which is going to be 10 to the minus 9, which is a nano. So 11 divided by 1.4 is 7.9. And then a micro divided by a kilo is a nano, okay? So that means that the current as a function of time is I naught e to the minus t over tau, which is going to be 2 milliamps times e to the minus t over 7.9 nanoseconds. Okay, so the time constant is setting the scale for how quickly the inductor's current is going to go to 0. So if I asked what was the current after 1 second, 1.1 second is many time constants, right? A nanosecond is a billionth of a second. So that's many time constants. So after 1 second, the current would basically be 0. Okay, it would be extremely close to 0. But maybe we want to ask the question, well, how much current is flowing through the inductor after, I don't know, 12 nanoseconds? That makes sense because 12 nanoseconds is comparable to the time constant, okay? If this time is too large compared to the time constant, then you're going to have a current of 0. Okay, so in that case, I would have I of 12 nanoseconds is equal to 2 milliamps times e to the minus 12 over 7.9. So notice how the nanoseconds canceled out because I had nanoseconds in the numerator and nanoseconds in the denominator. So that makes it easy. Let's see. 0.44 milliamps. That would be the current. Okay. So I want to, because of Christian's question, I thought of another one that is a little bit tricky that's sort of like this. So let me draw it really fast here. I'm almost done. What if you had a circuit that looked like this? Maybe this is 1 ohm, this is 1 ohm, and maybe this is 6 volts. Okay, and I wanted to know, if the circuit has been on for a long time, what is the current through the inductor? Well, in this case, after a long time, the inductor will behave like a wire, just a wire with no resistance. So if you imagine current flowing out of the battery, okay, it's going to hit this junction and all of it will choose to go through the inductor because the inductor has zero resistance after a long time. So that means that none of it is going to go this way. All right. All the current will go that way. So this resistor is basically made irrelevant by the inductor. Okay. So the amount of current that flows, it would be V over R. It would be 6 over 1. 6 amps would be flowing through the inductor. None of it would be flowing through that 1 ohm resistor. Okay. So I just wanted to point that out because the inductor isn't in series with anything. In this case, it's in parallel with something else, but yeah. All right. Well, that's my lesson for today. I hope you understood. I hope you enjoyed. Tomorrow, we're going to talk to you tomorrow.